So here comes the moment that many of you have been waiting for, which are some shortcuts to finding derivatives. And we're going to use what we learned in the preview activity to set up some rules when we're finding these derivatives. So the first rule is what we call a constant function. If you have f of x equals c, where c is just some number. If you think about that line for a second, f of x equals 7, f of x equals 10, it's just a horizontal line. And the slope of that horizontal line at any point on the line is going to be 0. So what we can say is that if we have this constant function, f of x equals c, then, for any real number, then f prime of x, the derivative, is going to be 0, always. All right, so if f of x equals 7, then we know without a doubt f prime of x is equal to 0. That's going to be the shortcut, but we know why, because we have that horizontal line, and the slope of a horizontal line is always 0. In Leibniz notation, we would say the derivative of radical 3 with respect to x, even though you say, well, there is no x, right? That's because it's a horizontal line. The derivative of radical 3 with respect to x is also equal to 0. So there it is in both notation forms. Now, the power function is what you were working with during preview activity 2.1.1. If I have f of x equals x to the n, and we call this a power function because it has some sort of an exponent up here, a numerical exponent, for any non-zero real number, if f of x equals x to the n, then f prime of x is going to equal n times x to the n minus 1. And you saw that happening right at the end of the preview activity 2.1.1. So for example, and we're going to start with a pretty tough one here, if g of z equals z to the negative 3, then according to this power rule, I'm going to bring that negative 3 down in front for a coefficient, and I'm going to subtract 1 from negative 3. Well, negative 3 minus 1 is negative 4. So the derivative, g prime of z, is going to be negative 3z to the negative 4. All right, let me get my picture out of the way here. In Leibniz notation, if h of t is t to the 7/5 power, then dh dt, the derivative of h with respect to t, is going to be 7/5. We're going to bring that exponent down in front. This exponent here comes down in front. 7/5, and then I subtract 1 from 7/5. Well, 7/5 minus 5/5, which is 1, is equal to 2/5. So h prime of t, or dh dt, is going to be 7/5 t to the 2/5 power. Okay. Now, the next rule involves an exponential function. And this one, we're going to give you the rule, but we're not going to tell you exactly why just yet. So you're just going to have to trust us on this one. For any positive real number a, if f of x equals a to the x power, now this is an exponential function because the variable is in the exponent, a to the x, then f prime of x is going to be a to the x times the natural log of that number, natural log of a. We're not going to show you exactly why we're getting that natural log, just again take our word for it for right now. So in this case, if f of x equals 2 to the x power, then f prime of x is going to be 2 to the x times the natural log of 2. If p of t equals 10 to the t power, then p prime of t is going to be 10 to the t times the natural log of 10. Okay, now, if we're dealing with e, all right, the base of a natural log function, and I'm going to talk about this in a little bit more detail in a few seconds, then the derivative of e to the x, which is an exponential function, with respect to x, is going to be e to the x times the natural log of e. But you may or may not remember that the natural log of e is equal to 1. And that might not make sense to you right now, but it soon will. So since the natural log of e is equal to 1, we can just say that the derivative of e to the x is actually e to the x. And that's a very unique function. This is one of the few functions where the derivative is equal to the function itself, which is a pretty big deal when we do a deep dive into that. Okay, so power functions, exponential functions. Power functions is where we have the exponent is a constant. all right, or a number, x squared. An exponential function is where the x is in the exponent, all right? And you have to keep these two things separated in your head, power functions versus exponential functions. And we will stop there.